Welcome to a new episode of the Asianet News Science Talk. Lung cancer is the second most common cancer worldwide. Also, it's the leading cause of cancer deaths globally. The 5-year survival rate is 20%. If it is detected at the early stages, then the survival rate is 60%. But if it is detected at late stages only, then the survival rate is 6%. So, the early diagnosis and effective treatment are the key factors in the battle against cancer. And the happy news is that a team of scientists from IISc Bengaluru invented a novel method for the early diagnosis and effective treatment of lung cancer. Their research paper, published in International Journal Applied Nanomaterials last month, and the corresponding authors of the paper, Professor Ashok M. Raichur and Dr. Jayaprakash, are joining us now from IISc Bengaluru. Welcome to Asianet News Science Talk. Let me introduce you for the viewers first. Professor Ashok M. Raichur is the head of the academic group of Materials Engineering at IISc, and Dr. Jayaprakash is assistant professor at the Department of Instrumentation and Applied Physics, IISc Bengaluru. Let me begin with the crucial question, that is, what hope you give us for the public, the battle against the cancer, especially lung cancer.
So lung cancer is, as mentioned, is one of the very, prominent cancers that is present, and difficult to treat, difficult to diagnose, and then treat it. So in order to have a better survival rate, we need to increase the chances of detecting it at an early stage. So there are methods that have been being developed by people to improve these existing systems. We have treatment methods, but we don't have enough methods to diagnose this disease quickly or at an early stage. So in that respect, our work tries to combine both the diagnostic component as well as the therapy component together. There are systems available which do these separately, but our system will offer the dual advantage of having both the diagnostic part and as well as the therapy part combined into one. So we use a photoacoustic imaging system, and simultaneously we also have a photothermal treatment system. So this is a kind of system which we think in the coming days. Of course, we need to do a lot of studies. We are currently still at the lab level, but we hope that if we are able to successfully reproduce this in animal models and then take it to clinical trials, we do hope that it will make the treatment of patients, so the patients become more comfortable with the treatment, and we hope to achieve a much higher success rate in both diagnosis as well as in treatment.
Professor Ashok, usually lung cancer is diagnosed at late stages only. Why it happens so?
The problem with many of the cancers is the cancerous cells are not easily accessible or they are not easily detectable. So usually when we detect the cancer, it is at a late stage because at that time the cancerous cells would have moved away from the original part of the body, and what we call as metastasis, and they start moving in other parts of the body, and it is then that we start discovering them much easily. So that is why at that stage, what we call as the third or the fourth stage, it becomes late. Whereas in the early stages, they are confined to one part of the body or they are present in very small numbers, the cancerous cells. So it is very difficult to detect them easily when in the early stages. Only when they multiply and become in large number and become large, or sorry, they multiply and they start manifesting in large numbers, then we start detecting it quite easily. And by the time it will be too late.
Dr. Jayaprakash, what merits you see in your method when compared to the existing methods for the early diagnosis of lung cancer?
Yeah. So if you look at the existing methods in the clinics, right? So you have multiple approaches. Basically, you have X-ray, CT, and you have positron emission tomography and MR, right? These are the standard methods for observing cancer. And if you think about it, all of these are coming with some or the other disadvantages. So if you look at X-ray and PET, these are using ionizing radiations or radioactive elements, which are harmful to the body. And even if you look at MR, standard MR cannot distinguish tumors so easily. So what happens is you need to use some kind of contrast agents and so on. And specifically for lung, it's even more difficult with MR kind of an imaging technique. So you need, and even ultrasound, because lung has a lot of air, you cannot use ultrasound as well. So with this particular technology, you have all these disadvantages which could be overcome. And at the same time, this is also kind of low cost and scalable technology.
Please explain what is this photoacoustics method, or what principle you use in this.
Yeah, photoacoustic method is basically a hybrid technology. So wherein you're going to shine the tissue with the light. So we use something called as a pulsed light. So this pulsed light has the pulse width of 10 nanoseconds.
You use light to fall on the
tissue.
tissues. Okay.
On the tissue.
A
And
normal
this
light or
has,
laser?
Yeah, we use laser light, and this light has a pulse width of 10 nanoseconds. You can imagine that we're illuminating this particular tissue to an order of only 10 nanosecond time scale. So what happens is within that time scale, you have the tissue which will absorb the light and then generate sound waves.
So the light is converted into heat energy falling upon the cancerous cells, and that heat is converted to sound energy.
Correct. Okay. That is a pipeline, but the amount of heat which is being generated is in the order of millikelvin. So you can imagine that it is safe. It is not really a lot of temperature that the cells are dying at that thing. But for the photoacoustic effect, you require that temperature to be in the order of millikelvin. The more important thing is you need the heat and the stress to be confined within that particular tissue. So what happens is, since these two are confined, and as soon as the light illuminates stop, you'll have acoustic wave, pressure waves that is generated. And we detect these pressure waves using ultrasound transducer.
Let me ask you one doubt. Why the healthy cells not generating heat, only the cancerous cells generating heat upon falling a short beam of laser for a nanosecond?
Yeah, that's a good question. So basically what happens is, we are not really looking at cells, we are looking at molecules. So by molecules, what I mean is you have different molecules in the body called oxyhemoglobin, deoxyhemoglobin, glucose, lipids, and so on. Each of these molecule absorbs at a particular laser wavelength. So when I illuminate it, I will illuminate that particular tissue at different wavelengths, and I try to resolve these different molecules. And there is a theory which says that at the cancer site, you have more requirement of more oxygen. As a result, your concentration of oxy and deoxyhemoglobin tends to be different in cancer compared to other tissue types. So that's how we try to measure something called as an oxygen saturation map. And from oxygen saturation map, you can identify the tumor site very easily.
So this gives a better picture of the cancerous cells, and the doctors can diagnose from the very early stage of the disease, right?
Yeah, because you can identify the cancer tissue variations at the cancer site, but the oxygen saturation maps will be very different at the cancer site compared to the background. That's what gives you a contrast in photoacoustic imaging, and that can be used for early detection as well.
So from the first stage itself, with your method, the doctors can identify the lung cancer?
That is a difficult question. The reason is, the point is, most of these cancers, right? And the patients come to the clinic after a certain time, right? After the symptoms arise. But by the time that you have the symptoms coming up, right? You know that there is some the cancer progression is happening. Okay, so early detection is still a challenge, because most of them are not aware of when to go to the clinics.
So the symptoms appear only at third stage onwards, not in the early stages.
Not in the early stage.
So how will
that is the reason
So how will the public know when to screen for lung cancer?
Correct. So that is the reason. In the first, what they do is, for example, if you have breast cancer as an example, they recommend 2 mammography scans or you have to do screening every year, okay, so that you can identify breast cancer and these kind of cancers. So now that kind of screening programs has to come up even in our country. So the other alternate technologies, you have to convert these systems into wearable systems. So by wearable, what I mean is, if you are able to make uh, these photo acoustic technology as a wearable technology, then you can think of identifying these biomarkers at your house in some sense, but you cannot do clinical interpretation of it, but rather you can get a signal that you have to go to the doctor, right? So that could be possible by developing advanced wearable technologies and then looking at this market.
Will you explain the guidelines for the public for to check at the home itself, that is whether they have any symptoms for this lung cancer?
So typically the symptoms of lung cancer appears by coughing and so on, right? And the point is, unless until you have symptoms, very difficult to check. Okay, the actual issue is that once you have this kind of lung cancer or anything related to lung, you'll have difficulty in breathing. So that is one symptom which
So
you
difficulty
need to,
in breathing is the first symptom.
Yeah, it is one of the symptoms, and the other symptoms is you will have cough and all these aspects which is related to breathing, right? That is one of the symptoms which people have to look into.
Professor Ashok and Dr. Jayaprakash, you both are from engineering fields. So we would like to know how you conduct this research and experiments in the medical field. And Professor Ashok, your expertise lies on materials engineering, especially nano materials. So we would like to know how you focus or how your lab focuses on the experiments for this method.
We have been working in the area of nanomaterials for about close to 18 years now, and we have developed many different systems for drug delivery in the past, and we continue to do that work. Parallelly, we have also started working on using these kind of materials for photoacoustic imaging as well as photothermal therapy. We have tried other materials in the past, but were not successful. But then this material we started getting success.
What's the speciality of this material you use, these nanoparticles?
This particular composition, for example, copper sulfide, or there's a class of materials called chalcogenides. They have been shown to exhibit this the property of photothermal therapy in the past. Similarly, gold separately has been used, but the disadvantage is gold will start functioning or having these properties at a much larger size, or particle size. So I am talking about a couple of 100 nanometers. So when you have larger size particles, they are difficult to deal inside the body. So somehow if you can reduce the size of these gold particles and also combine them with copper sulfide, that is the idea we came up with. So we developed a method of synthesizing copper sulfide and gold, which is coupled together. And then we were able to reduce the size and also have the synergistic effects of both these particles. So that is the uniqueness of this study.
So what motivated you to combine these gold nanoparticles and copper sulfide particles to get a hybrid of these two, that is gold and copper sulfide nanoparticles?
Yeah, as I just mentioned.
What motivated you to get this idea of making the hybrid of these nanoparticles?
Yes. Basically, as I said, gold works well, but at a larger size, and handling it at that size is slightly difficult, especially in vivo condition. That is when you inject the sample inside the body, and you also need a large amount of energy for it to function, to generate heat inside the body. But if you reduce the size, then normally the nanoparticles tend to function better, in terms of the reaction to the light. So copper sulfide has been shown to do that, but then there are other challenges with that. So what we did was, if you could combine these and enhance the signals that are coming out from the particle. So we thought of this idea. So can we combine these two somehow? And so we developed this method of synthesizing. And then when we tested it, our hypothesis was indeed correct, that we started getting enhanced signals, both in terms of the acoustic imaging as well as the photothermal therapy. So that was the motivation behind the study.
Dr. Jayaprakash, your expertise lies on computational methods and photo imaging. So, or how these expertise help you in conducting research in this field, in this medical field?
The area of computing is revolutionizing all the aspects of medicine. Let it be areas of like radiology or you have digital health and all these different topics, right? All this is being transformed. So if you go back, if I can go back to my own career, right? Initially, I was a computer science student where I was working on developing algorithms which are related to things like automatic segmentation and so on, right? If you can relate it to 10 years back, there is very less interest in those topics because most of them were working with traditional models. Now, recently, what has happened is you have this deep learning and artificial neural networks, and these kind of technology which has come up, and they have advanced methods to detecting these tumors and doing accelerated reconstructions and so on, right? So these are different challenges. For example, if you look at CT problem, in computed tomography, one of the important challenges is how to reduce the dosage, radiation dose under the patient. And in MRI, another challenge is how can I acquire the data faster, right? So these challenges were overcome by computing methods, right? How do you overcome it? Is basically try to identify data which is relevant to collect, and then use that data to generate information which a clinician wants. So that is the kind of approach which is being considered. So as a result, there was a smooth transition for me from my background to move on towards medical imaging and these kind of technologies. And even if you look at surgical interventions and so on, right, you have a lot of technologies like robotics and AI, which is playing a crucial role in surgical intervention as well, because it's very important. You have fluorescence guided surgery where they are trying to identify these cancers during surgery, because if you don't remove all the cancer tissues from the body, there is a very high chance of reoccurrence. So to avoid that, they're trying to use imaging and augmenting it with surgery to allow for improved surgical outcomes. There is a natural connection between the area of computer science with and electrical engineering with medicine. So that's how I moved on to these kind of technologies.
So you use the principle of photophonics, which was invented in 1880 by Alexander Graham Bell, which he considered as the greatest discovery more than the telephone. So this principle is used in photoacoustic imaging, right?
Yeah, that is the principle. So if you think about Graham Bell, right, in those days he didn't have a very sharp laser. So the experiment that he conducted was you had this sun, and he used to illuminate this sunlight onto metal, and he was chopping this sunlight, and that generated the sound waves. So that was the initial discovery of how you can generate sound from light. And now we have advanced technology in terms of laser and lasers and so on, which happened in 1950s, 1960s. So now you have wide variety of lasers, like you have supercontinuum lasers, pulsed lasers, continuous wave lasers. So now you have different lasers catering for different applications. So the evolution has started in 1980s, but it has grown much farther. And more recently, you also have multimodal imaging systems that has been considered. So that is, for example, if you have ultrasound, which is already there in the clinic, right, which is used for examining fetus and different parts of the body. So now people are trying to combine these ultrasound scanners with photoacoustic technology as well. So there you just need to append a laser into this technology, so you can get both ultrasound data as well as photoacoustic data. So ultrasound data gives you some kind of structural information, and photoacoustic data will give you molecular information like oxyhemoglobin, deoxyhemoglobin, and so on. So you can put molecules on the ultrasound image and then show it to the clinician, which will be much more advantageous in terms of diagnosis and monitoring.
So, just as the invention of laser revolutionized this photophonics or Raman spectroscopy, just how this artificial intelligence revolutionized the current fields you mentioned.
Yeah. So artificial intelligence is, as I told, is revolutionizing medicine. So for example, I can give a simple example of CT, X-ray CT. So if you think about it, the amount of dose that was deposited on the patient was huge in CT. So now, because it depends on how many angles you are acquiring the data from. So with AI, they have shown that I need only few projections, maybe up to 5 or 10 projections, rather than taking 180 projections. And this reduces the dose, if you can think about it, by about how much, 30 times. That is a lot of dose reduction, and that will allow you to do CT multiple times. That is the first point. And the second point is it'll also enhance computer tomography as a adjunct modality also for for all kinds of scenarios. Okay, so like similarly, if you think about other areas, like as I was telling, robotic surgery is also another area, right? If you think about it from the perspective of robotic surgery, it is also assisting the clinician, but during surgical intervention, right? So you want to make these kind of systems, robotic systems, more and more. You have to give as much data as possible. So the way you can do that is acquire as much data as possible and feed it to a deep learning network or an AI model, and then these robots can do more intelligent tasks. Okay, so this is another application, right? And if you think about something like neuroimaging, so neuroimaging is also another area where there is a lot of computations involved, because in tasks like fMRI, cold fMRI, and so on, where you want to know the activation of different neurons and so on, there you need to do a lot of statistics and computation. So now people have also tried to use AI to do this fMRI and see if it can really help and so on. So any imaging technique that you're taking is being influenced by AI. Not only imaging, even at signal level. For example, if you look at ECG, EEG, and so on, right? These signals are also very essential in clinics. So these signals are also being used and being classified into different disease conditions. For example, in ECG, if you look at the signal, you can classify it into arrhythmia and something like lower bundle branch block and so on, right? Myocardial infarction and so on. So now if I have good amount of annotated data, I can use EEG signals to classify this and then reduce the intervention of a clinician. But at the end of the day, someone has to take responsibility. So these technologies can assist a clinician. It can give you some information, I would say ground zero level information to the clinician, but then the clinician should take it forward from there and do appropriate diagnosis or treatment.
Professor Ashok, the other authors of the paper are Madhavi Tripathi and Swati Padmanabhan. What's their role in this research?
Madhavi Tripathi is my student, a PhD student working in my lab, and Swati is a PhD student working in Dr. Jayaprakash's lab. And Madhavi's role was to prepare she actually came out with this initial idea of combining these particles.
It's her idea, that's the combining these particles.
Yeah, the way we progress in PhD is that we allow the students to come out with some kind of idea. They do a literature survey and they come out with some broad idea. Then we sit together and we define a problem. So that is how this problem was defined.
That's great, sir.
And then
you give space to your students' idea.
Yes. All the students have to define some kind of problem, and then we help them to shape it up, and put it in a proper order. And then she has done all the synthesis work, the characterization of these particles in terms of the biological work, and then the photoacoustic and then the photothermal work was done under the supervision of Dr. Jayaprakash in his lab, where Swati played a crucial role in helping her out. So that is how this collaborative work has come about. So this is a true collaborative work, and it is interdisciplinary also in nature.
So, what are the challenges you faced during these experiments and finally publishing it?
Yeah, there are always challenges. The initial part of the challenge was synthesizing. When you synthesize particles, typically the way we synthesize particle is we start from solution and we start precipitating them out. And during the process of precipitation, the particles will start growing. They start becoming bigger and bigger. So there should be a way of controlling the size of these particles. So that is where the challenge was, and we were able to achieve that by using different chemicals in the synthesis process, and then coupling it with gold. So we defined this method. It took us some optimization to do that, but finally we arrived at the right proportion of the chemicals, so that we could synthesize them quite effectively. Not only synthesize it, but also reproduce it.
Dr. Jayaprakash, do you see any areas which you need to improve in this research to get a better result, which equip you to go to the next level?
Yeah, so that's a good question. So as I was telling earlier, right, if you think about it, for example, you take lung cancer, any cancer. So identifying it early is a very important, goal, right? End goal. So there are two ways of looking at it. One is from the probe's point of view, which is develop a nanoparticle or all these particles and evaluate the translatability in terms of cytotoxicity and so on. So these particles should not trigger something called as immune response in the body, and that will be a very challenging task in terms of translation, right? So now if you think about it, I want to develop a particle which does not trigger immune response. So for that, you should have particles which could be from biological origin. That is one direction which people can take. So which could be like plant-based, bacteria-based, or animal-based kind of particles, which could adopt to the body a bit more easily than particles which are inorganic or synthetic and so on, right? So that is one direction which people are looking at. And the other aspect, as I was telling, is to build devices which are variable in nature. Why variable is important is because most of the times people are not really aware of how their health status is. So that is the reason developing variable technology and building variable systems is very, very important. And the market is also towards variable. Most of them are now, if you think about it, if you take continuous glucose monitoring as a simple example, that market is growing very rapidly with time because it has a direct link to diabetes and so on, right? So similarly, every disease, even if you take cancer, there should be methods which are systems that should be variable in nature, and it can give indication of for you to go to clinic and do a regular health checkup. So that is more important, because once you have that kind of penetration of knowledge into the general public, so then you will have early detection of these kind of diseases, and that will help us in terms of treatment also.
Professor Ashok, do you find any potential application for your method to treat any other cancers in future apart from lung cancer?
Yes. In principle, yes, we can treat it for any kind of cancer. Even if you are just want to image a certain part of the certain tissues in the body, we can still use it without having to use it as a treatment method. So there are several applications that are possible using this technique. So that is not a problem. The other advantage or the next step would be to also combine these particles with a drug molecule. Supposing if you are able to attach a drug molecule onto the top of this particle, then we can combine the effect of both, let's say, chemotherapy as well as the photothermal therapy together to achieve better efficacy in treating the cancer cells.
So that's the future of your method.
Yeah, in fact, we are already working on it. We have started that work parallelly. So that will be the next step. As far as this particular work is concerned, we'll now start working on animal models, and then we will see how the data comes out. Once we analyze that data, then we should have a better idea of moving to the clinical trials.
So, when the public can expect the ready-to-use technology for diagnosing the lung cancer using your method?
Yeah, normally these processes are a little long drawn. So typically, developing a new process typically take about anywhere from 5 to 7 years, I would say. But that is once we come into the clinical trial. The clinical trial themselves will take at least 3 to 4 years.
So, you
then
need collaboration with hospitals for clinical trials.
yes.
So,
We,
is
we,
there any
we have to
collaboration
collaborate
now?
with the clinicians. Yes.
Is there any collaboration now?
Not right now, but we hope to do it in the coming months.
Any
Once
discussions?
once we do the animal model studies in IISc, then we will start talking to people and see how to take it forward.
Which hospitals, sir?
We haven't. There's no particular hospital identified right now, but normally we work with either St. John's or with Ramaya Hospital, which is next to us. So we hope to do that in the coming months. And in the coming years, we are hoping that we are starting our own medical school. So in the coming years, I think we should be able to do it within IISc.
IISc will start medical school.
Yes, it is a process that is already on, and we should have it next year, end of next year.
Will next year you will start medical school?
Yes, yes.
Okay, that's a great information. Professor Ashok, you received many awards and honors. We cannot list all those in this interview, including the Fellow Royal Society of Chemistry in UK and almost all awards in India for the scientists. So, and you are visiting professor across in many universities across US, Germany and South Africa. So, how this vast experience helps you personally and professionally, and most importantly, how much your students at IISc benefit from this experience?
Okay. In terms of collaboration, this is a very unique thing that is to academicians. And in IISc, we have a lot of visitors, both to my lab as well as to other labs. So we get to hear ideas and also exchange ideas with the faculty. And they also, when the faculty visit us or we visit the faculty abroad, we tend to interact with the students also. So from the students also perspective, we tend to learn a lot, and my students learn a lot from the visiting faculty. So this is, and it also helps them to grow as as researchers, because they tend to get, when you see a different line of thinking, a different kind of work or expertise, and then when you try to bring it into your own work, I think that really helps. And I would say that my whatever my collaborations, my friends or colleagues who have come here and visited us and stayed with us, they have always helped my students, and that has also helped them. We send them abroad sometimes to do some work in different labs. Not only with the collaboration outside India, but also within India, we have collaborations. So these kind of collaborations help us to strengthen our research and also help us learn better, and progress quickly into whatever we are doing.
So, for science research, borders don't matter, only humanity.
In fact, now I would say that if you take IISc as an example, IISc is a leading example where there are no borders between departments. So we work across disciplines, we work across departments, and that has now transcended into other institutes also. As we look across India as well as abroad, there is nothing like, for example, a chemical engineer can work with us, or we work with chemical engineers both in biology as well as in classical areas. And material scientists are now working in the area of bioengineering. So these kind of, now we see computer science and then electrical engineers. So these kind of multidisciplinary setup has now helped us not only to do research, but also enhance, especially in the field of medicine, both in terms of treatment and diagnosis.
So, Dr. Jayaprakash, you also received many honors and titles, and you guided many students also. So, comparatively at an younger age. So, you had vast experience in diverse research fields, both in industry and academia. So, and also you have much experience in the Munich Technical University in Germany. So, how those experiences help you in this research in medical field?
So in Technical University Munich, what happened is that group was much more highly interdisciplinary, where you had chemists, biologists, engineers, and everyone, right? And that was a much larger group. It is a big group of about 70 people. And there, what I have learned is creating such kind of an environment will allow for easy communication between all these different participants. And more importantly, there was a hospital, and in that hospital setting, that we had a lab also. So, and you are talking to the clinicians over lunch and so on, right? So that will help us in identifying the clinical challenges and then solving relevant problems, which will help improve the clinical workflow and so on. So that I am seeing that might happen in IISc, and this will be the one of the first places in India that where it will happen, where you'll have a new medical school that will come up, and then you'll have a interaction with the clinician and the engineers, life science experts, and all different kinds of people, right? And that will what will accelerate discovery towards improving health and other aspects of health. Yeah. So I think the most important thing is to create that kind of ecosystem where you have people coming from different backgrounds, discuss, and then that will make sure that you'll have some ideas that will be generated which is relevant to the actual real world problem.
Professor Ashok, can you share your hopes and expectations on the future impact of your research on the healthcare and the patient outcomes?
As I said, I have been working in this area of trying to use materials for the betterment of, let's say, the drug delivery and diagnostics for about close to 18 years now. And I have done all my work normally ends at animal models, in the earlier stages. Now we have reached a stage where we can take it to the clinical trials. So I hope that, and much of our work has been highly appreciated, and we have got very good results. But unfortunately, we are not being able to take it further. So I do hope that in the coming years, before I retire, I hope that I will be able to transform at least one of the technologies that we have developed in-house to be able to, let's say, at least do clinical trials, and if successful, then we can go in for a commercial product. If I can achieve at least one of it, I think that will be a great recognition or a great achievement, I would say.
Let's hope so, sir. And Dr. Jayaprakash, what's your hope and expectations?
Yeah, there are two things. Firstly is the hopes and expectation for healthcare is one aspect. The other aspect is hopes and expectations for education. So hopes and expectation for healthcare is basically try to develop a device which will be point of care and that will allow for early detection. Okay, that is my hope, to see that at least by end of the career I have one device which is commercialized, and that I think is the hope for most of the academicians in India, so that at least by retirement there is something which will contribute back to the society. In this case, it will be healthcare, and the hope is that for the education aspect is that we want to have more and more students getting into these areas, and that will help. That will basically help the knowledge to trickle down to a lot of people, and that will also help in bringing awareness among general public. So education is a very, very important tool where we encourage more and more students to join these kind of programs, which is there are new programs like MD PhD and MD MTech which is coming up in our institute that will help them to really become a clinician, but at the same time how can we use the engineering aspects also, right? These kind of tools will add value in the clinical setting as well. So in terms of education also, there is a lot of motivation needed for students to enter into this space, right? Yeah, so that is what is my hope, that I'll have more
and also
more train more students and create a space for them to find relevant job opportunities both in industry and academia.
Professor Ashok, I think your comment points to the need for more industry-academia relation for bringing the technology of the basic science research.
Okay. See, industry should also actually be an equal partner in developing technologies. Even though the ideas the basic ideas and the applications are demonstrated by universities or institutes at some level. But eventually, I think we need some hand-holding from industrial partner, which can help us to commercialize, move it to a larger scale, pilot scale, and then probably take it to the commercial level. So the industry interaction is always a must. At some point of time, either after patenting the technology, we can take it further with the industrial partner, or if if the industrial partner is present from the beginning, that also is a good sign. Those kind of interactions have now become more and more in all our top-notch institutes in India, and we hope that we should be able to collaborate with somebody in the coming days.
Thank you very much, Professor Ashok and Dr. Jayaprakash, for finding time and sharing information with us. And we wish you continued success in all your research projects, and we express our gratitude for working for the betterment of our life. Thank you very much, sir.
Thank you so much.
Thank you, Shalini.